Maybe.
Maybe.
Thank you, Glen.Mabey, who is going to talk about QNDArray, which is a Numpy clone for C++ and Qt.
Thank you. And I am very happy to be here to share my work on this C++ class, and hope you would enjoy it. Here's something we're going to talk about, and I'm sure that all of you are just asking, why would you try to reinvent the wheel? Why would, when we have all these facilities and toolkits, why would you go back? And I'll explain a little bit of that, as well as some of the helper classes that I've implemented in order to make C++ a friendlier, better place for Python programmers. I've been writing C++ for so long now, it seems like I'm kind of out of touch with some of the recent developments in NumPy. And so if I say things that are wrong, please correct me, maybe after. This is to the best of my knowledge. I have uploaded my source code to the Qt tutorials repository. If you want to take a picture of this with your smartphone and download it right now, you can follow along and browse it. That's fine, but we're not going to spend a lot of time on this slide. So, because of where I work, I have to program in C++. It's not really much of an option. And so, back in the day, I thought I was going to just be a Python programmer and with implementing certain algorithms in CUDA. And then when that turned out not to be possible or tractable, it was a big disappointment. And so I created this. It's a templatized C++ class called QNDArray. And I didn't want to reinvent the wheel, but I mostly didn't want to reinvent the behaviors of NumPy. I wanted to be able to use those things directly. And so if it's not mirroring the behavior, then I think it's a bug. And then NumPy also becomes a really natural framework for unit testing of this class. If you're not familiar with Qt, I used to be a GUI toolkit back in the Qt 3 days, and then they split apart the dynamic libraries so that you could write, GUI-less applications using this framework. And most importantly, most of these data container classes are reference counted. But we don't have a lot of the facilities that are fundamental to the operation and use of NumPy, so well, we had to start out by writing a tuple class. Kind of shocking to have to go back, that low level. But it's not, what I wrote is not reference counted, just the tuple isn't. It's a fixed size, and the data types are known, right? In particular, when you're indexing into a QNDArray, you're passing at this QNDA2 instance where the elements are all integers, guaranteed to be integers because of our compiler. And on 32-bit platforms, it's a 32-bit integer, and it's a 64-bit platform, it's a 64-bit integer. That's this QNDA size type. So, it's basically just a little array, but with things like negative indexing, which we have to have. We can't live without negative indexing, and a bunch of constructors, and a way to produce a QNDA2 instance of arbitrary length by passing in a list. And it's, it's just, you're looking at this QNDA2 less than 1 greater than, you're saying, that's just ugly. I know, I'm sorry. But, there's little shortcuts that I've tried to produce to make it a little bit less painful as we go along. And some little, utility functions on the tuple class instance itself. But we have to be able to store and access data and have it go away when the last reference is decremented, right? So we have this QNDA mem source class, which is going to take good care of pointers. When you instantiate it, you're going to give it a size, and then when the reference count becomes 0, it's going to free it, or CUDA free, or whatever that you want it to do. And we have to support memory mapped files. There's just no way to not support that. And we're going to use the platform independent classes in Qt to do all the dirty work for us. So we're still able to stay at kind of a high level with a lot of the things. And other classes that derive from QNDA mem source, like taking it basically from a string, a Q-byte array, or from some shared memory as we're trying to pass data around efficiently in the applications I work on. And of course, you can derive other classes from QNDA mem source yourself if you have some type of requirement. But here's just a brief example of 3 different ways in which to memory map a file to a QNDArray. Here's the straightforward way. You can see one way in which I tried to push the functions into these QNDA namespace instead of adding more and more methods to the class itself, just like Numpy has tried to do. And hopefully this syntax looks familiar to you: a file name and a mode and a shape, right? And then it reads it and then creates an instance of the QNDA mem source Q file. And when the last instance is destroyed, then it closes the file and goes away. That's exactly what we want it to do. But there's a lower level also which you can access it. You can open the file yourself, however you want to do that, or any QIO device, and pass it to a constructor. And this is code taken straight out of a project that I'm working on. Passing the file ID to a constructor with an offset and then a shape, and there you go, there's your instance. But you can also instantiate this reference counted shared or memory source instance yourself and kind of handle it at a lower level if you had lots of arrays that needed to access the same file, maybe in a different way. You could just run with one instance and then, of course, copy and increment the reference count each time you do. But automatically, you don't have to do that manually. And closes the other file and deletes the pointer when it's done, right? So, we've got this QNDArray class, which is templatized, or however you like to pronounce that. Inherits from a QNDArray base class, which took a couple years to find a really useful case, somewhere where I really needed to use that base class. It just didn't ever come up, even though I thought it would at the beginning. So each QNDArray base class has a QNDA mem source, and then all these classes that are running down here on the left-hand side are derived from QNDA mem source. And, it kind of just behaves how you would expect it to. But indexing was, if we have an array, we have to be able to index into it in some arbitrary number of dimensions. And the problem is that the bracket operator in C++ will only admit, a single argument, not very convenient. So the most basic indexing operation we do is to pass a full tuple in, which is the same size, same dimension as the array itself. And of course, you get a reference to the data element that you've indexed into. But when you want to get another array, it gets a little bit messier. You can index into it with an integer, and that'll return, as you can see from the function declaration there, another array of dimension 1 smaller, same data type. And this is where I perceived a difference and a problem with the multi-dimensional array class that's in Boost, is it didn't have this feel of this Pythonic kind of feel. It didn't look like it was handling the whole reference counted classes. Maybe I'm mistaken, but it didn't look like it was returning classes, instances like we would expect to handle in NumPy. Then we get down to n equals 0, of course, and then we just take a page out of the NumPy playbook. We basically have a 0 partial specialization for n equals 0, and a cast operator which takes you back to the original data type. So if you've got this one-dimensional array, A1, that you're going to index into with a 2 or a tuple, then it's basically the same. Slicing. Well, This is not a beauty pageant, gratefully, but we all know what this does in NumPy, right? Got this array, we're going to take the first two elements of axis 0, and then all of axis 1, and just element 2 of axis 2, and all that, right? And before I show you how that's done in QNDArray, cut me some slack here. This is an equivalent way to do this in Python, right? 3 separate bracket operators, and yeah, I know it's looking a lot more verbose. But this is how you would do it in QNDArray, right? So, right, gross. Look how long that is. It doesn't feel like NumPy, does it? Have to type all this out. Well, it was the best I could do because there was the fundamental decision to make it templated in the dimension, and so you have to specify the return type for a method in C++. And so you basically have to have type. So the flip side is you know exactly what you're dealing with. As you index, as you slice, you're always very much in control. It's a much more informed approach to writing this kind of code. And some shortcuts that are kind of painful. Okay, so if you want to understand something about how QNDArray works, you have to understand something about reference counting as it's done in Qt, which mostly is done using implicit data sharing. This is an example straight out of the Qt documentation. You got 2 pix maps, and then you share the data there with p2 equals p1. But then on that paint.begin line, as soon as you invoke a non-const operator on a method, it detaches it. That is, they used to share data, but as soon as you operate on one, it copies the data into a new instance behind the scenes, and away you go, modifying only P2. So that doesn't really match the NumPy way of reference counted objects either. We want to have the same feel to this data manipulation. But this is pretty prevalent in Qt. These are all the classes in Qt that use shared data. Okay, it's a lot. We're not going to go into that, but we're going to talk about how QNDArray does it. So this function is obviously intuitive to all y'all. If you don't want this function, eat it, to modify the argument that you pass to it, well, you're just going to have to copy it before you give it to it, right? And that's all fine and good. Here's 3 equivalent, well, not equivalent, but functionally, behaviorally the same prototypes for this function in C++. You could copy the whole instance in, and it's got a reference count to the actual data structure, so it's copied in the offset and the shape and the strides and everything, and then it's going to operate in the same data. Or you could pass in a pointer to it, which is the preferred Qt way, because you can see that you're passing your pointer in, so it's more obvious that you would modify it. Or a reference, right? It's all going to be the same. The problem is this const thing, which, seems really obnoxious, but in writing this, I really wanted to produce something that was acceptable to C++ programmers. It was actually felt like Qt at the same time. So when you do this kind of a thing, you pass in a const reference, because the copy constructor also takes a const reference, you can create this QNDA copy instance, which is now mutable. I mean, you can modify the data that you passed in you thought was const. So that's we're just going to have to live with that, actually, because of Visual Studio, actually. I won't get too much into that, but you can't have both at least as far as I can tell, a const copy constructor and a non-const copy constructor. Visual Studio just doesn't get it, just does not understand why you would ever want to do that. So This is one way, also copied just straight out of code that I've written, for mitigating that, a new method called const shallow copy. So this returns an instance with a flag asserted that's basically copy on write. So you're returning a QNDArray instance, which is not const, because even if you did, you could copy it and get a non-const version of it. But as soon as you invoke a non-const method on it, it copies the data and you go. It acts much more like the implicit data shared model in Qt. Thank you. So, you know, this is no attempt to reproduce all of the work that all these great developers have done over the years, but instead, right now, it's mostly just an n-dimensional data container. And of course, if you're going to write your own for loops in C++, that's mostly all you need. But with the ability to have the reference counted data and the slicing that some of us just can't live without, just can't do it. And there are a number of features that have been added to this that I'll just go through these here quickly to see what there really is here. I do have a bit-packed Boolean array, partial specialization for QNDArray, 32-bit words, hold the bits, almost all methods. Okay, so there's a subset of methods, right? Like anding and oring. You basically have to get your original instance into a Boolean type before you can do some of these things, which I feel is less ambiguous. It involves another step, but it's more explicit. You know kind of what you're doing. And those methods are only defined for the Boolean partial specialization of QNDArray. But almost all of them require that the bit offset into the first word, you know, your 0th element, is basically aligned at the beginning of your first 32-bit word, except copy, of course. We've got some unit tests, and right, if it doesn't have the same actual behavior as NumPy, then it's a bug. And here's a little kind of domain-specific language, I guess. It's more of a copy and replace, search and replace kind of a thing, where you can write this code and then it generates both Python and C++, and then you run them and then it validates that they're the same. So you got this regression testing going on. So here you can see you're generating a new instance called test array 1, TA1, using a range, and then you slice it, creating a new instance called TA2, and then that produces, I won't go through all that, it produces C++ code that looks like this. So this, I think, is instructive. You can see what this test code line was, what the generated Python code line was, and then what the C++ code looks like. Here we're generating we're doing an A range, right? And then we print it out to a file, and the Python reads it in and makes sure that when it ran this Python line, pi_ta1, that it's the same. Bounds checking, we have to do bounds checking, and the way that's currently doing that is using QAssert, which then turns into a no-op if you're not compiling debug mode, which, depending on your perspective, is a good thing. I think I'm still a Python programmer at heart, so I can't get away from having a dict. I just can't. So there is something that's somewhat like that called a QVariant map in Qt. But that code is not the real integration into a QVariant map or a QNDArray. That's not uploaded to the Qt repository right now. Float 16, I implemented a float 16 type, which is useful for the bandwidth and memory constrained systems that I work on. There's a position value class, which is immutable. So an arg max gives you back an instance of this to the position and the value, or if you're doing along a single axis, then it gives you an array like that. There's some tricks you can pull with templates, like here I've got a mean function, which is an additional template argument. You can specify the data type that you're going to aggregate and divide in. So an array of floats, here I've done a mean with a double, so it adds it up using doubles and does the divide and returns a double of the mean. a bunch of little convenience functions for handling those types of things. Until a couple of weeks ago, every QNDArray instance had a data member, which was a Boolean partial specialization, the same type. And that's, we're going to have to go through this. It's getting big. It's bigger than I thought it would be. There's a class I implemented that inherits from QTableView, so you can look at an array really easily. No performance benchmarks. So it's a start. It's an n-dimensional array data container in C++. For people like me that are stuck in C++ land. I'm sure you have my sympathy. Anyway, that's it.